All right, there's going to be quite a bit of labeling on your periodic table. Also, I want you to go ahead and if you have printed out the ion sheet, go ahead and get it out as well. All right, I want to do something that some of you may not like, but I'm going to do it and then you can fuss later. I want the back 2 rows to find a seat closer to the front. Real quick. Back 2 rows, find a seat closer to the front. There's 4 seats down here, easy. There's another 2 on the ends. Here's another one on the end. There's one on the end. So find a seat closer up front. Back 2 rows. Some of you can just climb over into the seat in front of you there. There's 2 seats on the second row here. There's 2 seats down here. All right, this is the ion sheet that you need to memorize. And I want to talk about the top part first because this is the part I don't want you memorizing. These are going to come from the periodic table, which is today one of the things we're going to be labeling on your periodic table. I want to just point out that these are all available on the periodic table to be found there. And that's why I'm saying don't memorize these per se, because you're going to find them on the periodic table. And I'm going to show you that today. The bottom part, however, the polyatomic ions, these are straight memorization, and I'm going to give you some hints on that. And then the back side, which is the transition metal ions, is also straight memorization. So I'm going to give you hints on both of these, on how to memorize these. So what I want to start with are these polyatomic ions. These have some similarities, and if you will make these notes, then I'll talk about them, and I think that will help you. So right here it says per is 1 more oxygen than 8, and hypo is 1 less oxygen than ite. That's what that says. So just copy that down. Per is 1 more oxygen than 8, and hypo is 1 less oxygen than ite. These are the only 2 positive polyatomic ions. So make a note that those are the only 2 positive polyatomic ions. Everybody else is negative. And then over on the right, what I have written, most of your 8 or ite endings have oxygen. Most of your 8 or ite endings have oxygen. most of the ones that have the ending ate or ite have oxygen. Ide endings do not usually have oxygen. Now, there are exceptions to this. So if you don't like exceptions, don't even write that comment. Just remember ate and ite have oxygen. And then the other really important one is all 8 endings have one more oxygen than their ite. All 8 endings have one more oxygen than their ite. So only learn the 8. Only learn one group. So learn the 8 endings. Now let me explain what we're talking about here. So I said most of your 8 or ite endings have oxygen. So look at arsenate, arsenite, phosphate, phosphite. Look at what they all have. What do they have, guys? Come on. Oxygen. Carbonate, oxygen. Chromate, dichromate. I mean, all of those have oxygen. All of those. Everybody that's called 8 has oxygen. Cyanate. The only exception is thiocyanate. It does not have oxygen. But all these, nitrate, chlorate, all those. And they're not, they're named exactly what they say. If you understand that 8 and ite have oxygen, then if it is chlorate, what does it have in it? And chlorine. Chlorine and oxygen. If it's sulfate, what does it have in it? Sulfur and oxygen. If it's arsenate, it has arsenic and oxygen. So don't let that be hard. Then if you pay attention to the 8s, you automatically know the ites. So let's say sulfate, you memorize sulfate. That's SO4 negative 2. Automatically, sulfite is SO3 negative 2. If you will just learn the 8s, that cuts out about 5 or 6 things to memorize. Because if you'll know the ite is one less oxygen, but everything else is the same. So if you know nitrate, over here, is NO3 negative 1, nitrite is NO2 negative 1. These need to be memorized, and I would suggest that you memorize these in chunks. That would be an easier way to memorize them than just trying to memorize them in some random fashion. I would memorize them in chunks. I would take maybe the ones that have carbon, which are acetate, carbonate, oxalate. Take your cyanide, cyanate, thiocyanate. Then look at your nitrate, then this perchlorate series. Let me talk about that perchlorate series for a moment. Per means one more oxygen than 8. So if you pay attention, here's 8, it's ClO3. You automatically know that ite will be ClO2 negative 1. So the per means one more, so it would be ClO4. Hypo means one less, that would be ClO. This trend or rule, I guess you might say, for naming, once you know that, you can figure out polyatomic ions that are not even on this sheet. For instance, if you know permanganate is MnO4, what would manganate be? MnO3 negative 1. What would manganite be? MnO2 negative 1. Hypomanganite would be MnO negative 1. Okay? So you realize all of those going down through there. Does that make sense? So there may be some on sapling, may not be any that are different than these, but if there are, knowing these rules, you should be able to figure that out. Okay? These are straight memorization. The back side is also memorization. There's a couple of little hints I can give you for these. Us is lower charge than the ick. The problem is there's no rule as far as it's always one less or always one more. It may be two less. But in general, the us is one less, or is less, not one, but is less than the ick. So if you memorize cuprous, then you know that cupric is the higher charge, cuprous is the lower charge. And then the easy one is the Roman numeral is always equal to the charge. Don't make that hard. So if it's iron 2, what is it going to be? What charge? Plus 2. If it's iron 2, it's plus 2. If it's tin 4, it's going to be plus 4. Okay? These also are straight memorization. However, some of these do have some tricks to them that we're going to learn later. The beginning of next week, there'll be some tricks I can teach you on these that are in addition to this. So why are we learning these? Let me go backwards for a minute, then I've got more labeling on the periodic table for you to do. But let me explain why we're learning this and kind of the picture of where we're going to go in the next 2 or 3 weeks before the next exam. Right now, we are going to spend a lot of time labeling the periodic table, and I'm giving you kind of pieces to help you get ready for nomenclature, which is the naming of compounds, writing formulas. Everything we label on the periodic table today is just a way to help you learn how to read the periodic table. And it dawned on me yesterday morning when I was teaching this, because the periodic tables that I'm going to have you labeled, or the things I'm going to have you label on the periodic tables, it's going to be a lot of stuff to label. And honestly, it's like giving you the rules of how to read the periodic table. And at first, you're going to be overwhelmed. And it dawned on me that it's almost like starting a new job. If you were starting a new job at a restaurant, and even if you were just going to be busting tables, there's definitely a system to busting the table, especially if you have to set the table back. Let's say you're at a restaurant where you not only have to clean the table off, but then you have to put the placemats back, and you have to put the silverware, and you have to make sure all the stuff's on the table like it's supposed to be. When you start at that restaurant, they're showing you, okay, here's your cart of stuff. You're supposed to do this on the table, clean off the dishes, and then you're going to go in the kitchen or wherever, and you're going to go in this cabinet, and you're going to get the silverware. Over there is the wash solution. Over here is the silverware. Don't forget the napkins are in that closet if we run out in the cabinet. I mean, if you've ever started a new job, this is how they are, isn't it? They're like going through all these different things, and you're overwhelmed thinking, how am I ever going to remember all that? And then as you keep doing it, and you ask a lot of questions, and you make a lot of mistakes, you finally get it, right? That's what is going to happen in a little bit when you're labeling the periodic table. It's going to seem like I'm just labeling for no reason. Over time, it's going to come clear why you're doing it, okay? The big picture is that we are going to be studying elements today, and that's going to be a whole lot of what we do in the next few weeks. We are going with elements today and looking at their protons, neutrons, electrons, things that you did, and some of you in middle school, some of you in high school, most of you in high school, if not in middle school. Then we're going to, on Thursday, talk about nuclear chemistry, so we're going to go actually inside the atom. Then next week, we're going to go with electrons only, pretty much, and talk a whole lot about electrons, figure out where every electron is, and it's going to get to the climax of being able to explain why these ions have the charges that they have. So it's, yes, right now I'm saying memorize these. But I will explain to you, and there will be this point, I'm hoping for some of you, I hope all of you, but I know I won't probably hit all of you, but it's going to come this point that you're going to have this, oh, that's why they do what they do. That will be kind of like, yes, you've got it, once you get to that point. And then you'll be ready to be able to put sodium with chlorine and call it sodium chloride, or calcium with phosphate and call it calcium phosphate, and know that there's 2 calciums that go with, or 3 calciums rather, that go with 2 phosphate ions. That's where we're going. Today, it's not going to seem like that. So bear with me, and that's why I'm giving you the overview before I give you the periodic table. Now, last thing on this, there is an ion quiz over these. Does anybody want to tell me what that ion quiz is for? Say it. Extra credit. How many points? 10 points. Do I give any other extra credit worth 10 points? In fact, I only give you 2 opportunities for extra credit other than tutoring. What are they? Perfect attendance and an ion quiz. Why do you think I give 10 points extra credit? It's that important. That's why I give it. It's that important. I'm willing to pay you 10 extra credit points to learn these, okay? So learn these. That's what I want you to do. Learn these. I'll give you more hints as we go. Now, I'm going to start you off with the ion periodic table. And I'm going to be quiet and get out of your way. And I want you to label what you see on this periodic table. Okay, so what you should have labeled. This entire column is +1, +2, -3, -2, -1. Zinc, cadmium, and mercury are all +2. Silver is +1, just silver is +1. Aluminum is +3, just aluminum, +3. Put the stair step in, if you haven't already. Put this stair step in, it comes to the left of boron. So put that stair step in. And the stair step is the dividing line between metals and nonmetals. So to the left are metals. So make a note. To the left are metals. Where are the rest of the periodic tables? Are there any left? None left? Okay. To the left are metals. To the right are nonmetals. To the left are metals. To the right are nonmetals. And the metals are the ones that become positive ions. So the metals become positive ions, and they keep the name when they become the positive ions. Nonmetals become negative, and their ending changes to "ide." Nonmetals become negative, and their ending changes to "ide." The transition metals for purposes of ions. The transition metals are this middle block all the way over to the stair step. So what I have circled in red, those are considered to be the transition metals as far as ions are concerned. And they can have varying charges, and they may need Roman numerals in their names. Those are the ones that we talked about that needed the Roman numerals. The exceptions to those are the zinc, cadmium, silver, and aluminum. I'm not going to deal with that much right now, though, because if you read your ion sheet, you're going to find that information on the back of your ion sheet. So if you don't get that part of it down, don't worry about it. We'll catch that later when you're studying nomenclature a little bit more. Any questions on what you're seeing here? Go ahead.
The transition metals like this, a line like over gallium, is that like part of it?
This, it's because aluminum is a fixed charge. This is strictly for charges because if you notice on the back of your ion sheet, you'll see tin is on the transition metal side of the ions. Again, I'll talk more about that later. That's not a huge issue right now. The main thing I want you to get off this is that metals are on the left side, nonmetals on the right. Nonmetals change to "ide" ending, which is all that at the top of the periodic table. Metals keep their name. And then the +1, +2, -3, -2, -1. All right, the next thing I want you to label. This periodic table is showing the differences between the metals and the nonmetals and the metalloids. Hydrogen is a nonmetal, even though it is on the far left-hand side of the periodic table. So it is a nonmetal. The other nonmetals are on the right hand of the stair step. What you see in green are gases at room temperature. This periodic table is also helping you. If you can see this periodic table better, see the red? Those are gases at room temperature. Mine are green, they're red over there. The blues are liquids at room temperature. So there are 2 liquids at room temperature, and there are 11 gases at room temperature. And then these that I have marked in red are the metalloids. So those are the metalloids. No. If you can't see it, come down here where you can see it better. Well, rephrase that. The video is going to be on Blackboard. So yes, you can watch the video and just pause it. Yes. So who are the two liquids at room temperature? Mercury and bromine. Who are the nonmetals that are solid at room temperature? Who are the nonmetals that are solid at room temperature? Straight nonmetals, not a metalloid, but straight nonmetals. Carbon is one. Boron is what? A metalloid. Boron is a metalloid. So who are the nonmetals that are solid at room temperature? Carbon, phosphorus, sulfur, selenium, and iodine. Do you see that? So that's, you're reading the periodic table. Which one of those surprises you that it's a solid at room temperature? Iodine. Iodine is usually the one that surprises you. Why? What do you think of as iodine? What you put on wounds? And it's a liquid then, right? That is a compound of iodine that's dissolved in water. So that's a solution of iodine. This is iodine, the element, and it's a solid. Iodine, the element, is a solid at room temperature. If you've ever seen a piece of coal, that kind of is what you're thinking of when you think of carbon. It's more than coal, or it's more than carbon, but that would be kind of a picture of carbon for you. Question. Iodine is a solid at room temperature. Iodine, selenium, sulfur, phosphorus, and carbon are all solids at room temperature. Everybody that's not marked is a solid at room temperature. So that means on this periodic table, what is hydrogen? What state is hydrogen? Okay, and then all the others that are green are gases. From that, and bromine's a liquid. So basically, from this point over, except for hydrogen and mercury, everybody else is what? A solid. So silicon is a solid. Why is it red? It's a metalloid. It's a metalloid, okay? We're going to talk about metals, nonmetals, and metalloids. So this will make a little more sense today. But right now we're just labeling. All right, the last thing to label. And this one is probably going to be the most to put on your periodic table. Again, it will be on Blackboard, so you can just look at the video later if you're not getting it all now. I would prefer you doing that instead of taking a picture, since we don't have a periodic table. So, look at this one, but I'm going to make it easier for you. Just watch just a minute before you start. This one is really not as hard as it looks. Do a couple things first. 1 through 18 at the bottom. Just 1 through 18, 1 through 7. And then 1A, 2A, skip the transition metals, 3A, 4A, 5A, 6A, 7A, and 8A. And then the blue names. Forget all of this. What is all this? That's the same thing I've already done. Okay? Gases, you've already done that. Non-metals are those in yellow. You've already done that. Metalloids, you already have that. So you are just doing what's in red, what's in blue. That's all you're doing. Okay? Let me read these if you're having trouble reading them. This says alkali metal. This is the name of 1A. Alkali metal. This is alkaline earth metal. Alkaline earth metal. You already have transition metals written. Then these are the easy ones: boron, carbon, nitrogen, oxygen. This word is halogens. 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 And this is noble gas. There's really no need to name boron, carbon, nitrogen, oxygen. They're self-explanatory. They're at the top. But halogens and noble gas. Roman numeral 1A, 2A, yes. Do 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. All right, let me explain what you're doing. The periodic table is laid out in rows that are called periods. The easy way to remember what a period is what is at the end of a sentence. A period. And how our sentence is written. Horizontally, right? So these are periods. So there are 7 periods on the periodic table, 1 through 7. And the columns are called groups or families. And so the group numbers, there are 3 different ways of labeling the groups. And that's the goofy thing, because you're like, well, why do we have to have? Well, really, though, if you are an aunt or an uncle, you have probably maybe 2 names. At least you put an aunt or uncle in front of your name, possibly. If you're a mother, you have your name and mom or whatever. So we have more than one name. Well, that's kind of the same thing this is. These have different names for this. The IUPAC method, which is what this is called, don't worry about the fact that it's called that. I'll tell you what that stands for, International Union of Pure and Applied Chemistry. That means it is the standard way now to name these groups. Obviously, it's the easiest, 1 through 18. That's easier than these others. But this is the standard way we name these. Why am I throwing out these older ways? The Roman numeral method is the North American method. By the end of next week, you're going to say, I know why she told me that. Because there's something that this 1A, 2A, and all the way to 8A is going to correspond to. And so you're going to realize why I did that later. The alkali metal, alkaline earth metal, halogens, and noble gases. Why am I having you learn those? Simply because those are real world words. Where have you heard of alkali or alkaline? Where have you heard those words? Nobody's ever heard those words. Where have you heard them? In your high school chemistry class. Okay, that's good. You learned it in high school chemistry class. Water or substances can be alkaline. And what's another word for alkaline? What does it refer to? Acidity or basicity? If something is alkaline, it's basic, meaning the pH. So alkaline solutions are what we nowadays call basic solutions, meaning they have a high pH, which we'll deal with later in the semester. Why do I point that out to you? Because where that term of alkaline solutions came from is because alkali solutions or alkaline solutions are made by putting any of these metals in water. Anytime you put potassium, sodium, lithium, calcium in water, any of these that you put in water, it's going to make a basic solution called an alkaline solution. That's where the term alkaline solution came from, was because of that. The thing you didn't tell me, which I thought you would say, is batteries. Have you ever heard of alkaline batteries? Nobody's heard of alkaline batteries. Okay. What do you think are in alkaline batteries? Possibly. What could be in an alkaline battery? An alkali metal or an alkaline earth metal. Okay? Where have you heard of halogens before? Light bulbs. What do you think are in halogen light bulbs? Halogens. Halogens would make sense. Noble gases. Who can tell me about the noble gases? Some of you have had high school chemistry. What do you know about the noble gases? They don't mix with anybody else. Were any of you invited to the baby showers or to Kate's wedding or whoever else has gotten married lately in the royal family? Did any of you go? Why not? They don't need you, do they? No offense, you matter. Don't forget you matter, but they don't need you. They don't need you. They don't need anybody, do they? They have it all. They don't need anything. That's why these are called the noble gases. And again, next week you're going to even know more of why they're called the noble gases. Because they don't need a mix. Why don't they need a mix? Stay tuned and you'll find out why they don't. Now, what are we going to test you over? What am I going to test you over on this? One simple thing I'm going to do is on a test I may say to you, what is the name of the element in the halogen family, period 4? Come on, guys, look at this periodic table. What is the name of the element in the halogen family, period 4? Bromine. Now, what I want you to do, 5 minutes a day, is all I want you to take, and you can do a lot in 5 minutes a day. You have periodic tables that are labeled. Hopefully you have it all on one periodic table. If not, maybe you have it on 2 periodic tables. Maybe you need to take or print a clean periodic table and put it all on one. Today would be good. But here's what I want you to do. I want you to spend 5 minutes every day reading the periodic table. Now let me explain to you what I mean by reading the periodic table. I don't mean reading the numbers. I want you looking at the periodic table, and here's what I want you to say. Doesn't matter which one you have it on. I'm going to pretend I have everything on this periodic table. This is what I want you to do to yourself, with yourself aloud. Calcium. Okay, calcium's a metal because it's on the left-hand side of the periodic table. It is calcium. It has the symbol of Ca. When it becomes an ion with a +2 charge, and it's in group 2, also group 2A, and it's the alkaline earth metal family, and it's in period 4. It's a solid at room temperature. Chlorine. Chlorine is a gas at room temperature. When it becomes an ion with the -1 charge, and I would say it's chloride. It's a gas at room temperature. It's a nonmetal, and it's in group 7A or the halogen family or group 17, and that would be period 3. Now, if you spent 5 minutes doing that, you probably could talk out at least 15 elements. If you spent 5 minutes a day for the next 2 weeks, by the time you take your test, you are going to be so much more knowledgeable. And the other thing that you're doing for yourself is, even if you don't have a good memory, I don't call myself and I don't have a good memory. But even though I don't have a good memory, if I spend time looking at the same thing over and over and over again, I, in a sense, start to develop a photographic memory. And then I can visualize where things were on this. So when you get your blank periodic table, what are you able to do? Label it. And you will be able to find what you're looking for. Okay? So spend time doing that. I think it will help you if you will spend time. Now then, let's pull out your notes. And let's start with what we are going to do on the notes and kind of explain this a little bit better. So the topic at the beginning is elements. I already mentioned that. What we want to do is learn about elements. We're not focusing on mixtures today. We're focusing on elements. We're pretty much done with mixtures. May mention it a little bit. Actually, one thing we will mention today about mixtures. But overall, we're talking about elements from here on out for the semester. So the 3 types of elements you've already labeled are metal, nonmetal, and metalloid. Real quickly, tell me some characteristics of metals. I'll start you off. Solids, most are solids at room temp, except who? Mercury. Okay? So metals are solid at room temperature except mercury. Tell me some other characteristics of metals that you know. Good conductors of what? Heat and electricity. Good. Okay, what do they look like? Shiny. And then what are those fancy words you learned in high school chemistry? What are some of their characteristics? They are ductile and they are malleable. I love that they're still teaching those fancy words. I know they're not fancy, but I always love those words. What does ductile mean? Can be drawn into a thin wire. And it's like every time you want to do that, you want to do this. It's like you just feel like you have to do that. Can be drawn into a thin wire. And then what's malleable mean? Can be hammered out into sheets or shapes. That's what it can be hit with a mallet. So those are the characteristics of metals that you already know. Now, alloys is a special word. I may have mentioned this word before. I don't remember if I did, so I'm going to throw it in here. What is an alloy? I said I wasn't going to talk about mixtures except right here. It's a mixture of metals. An alloy is a mixture of metals. And some examples of those are your jewelry. Almost all of our jewelry is alloys of metals or mixtures of metals. They're alloys. What are some other examples of alloys? Steel and stainless steel. Good job. The first class yesterday told me that too. And that was good. A lot of kids don't realize that. Stainless steel and steel, both are alloys. What are some other ones? There's some B words that are alloys. Bronze and brass. Good job. Henry Hardin Cherry statue. is bronze, I believe. So bronze and brass. All of those are alloys. And it's pretty neat. If you're ever bored and want to look up a little bit about jewelry alloys, you actually can find out what the metals are in the different jewelry combinations. Like 24 karat gold or 18 karat gold, it's not pure gold. Now, if you have gold from other countries, a lot of times the gold from other countries is much more pure than our gold. I have some students from Saudi Arabia, and their gold is more pure than the gold that we use, and their jewelry is slightly a different color, if you've ever noticed that. It's almost more of a copper color, but it's softer. It's much softer because it's more pure. It's got more gold in it. And the student the other day was saying, and it's more expensive, he said, which would make sense. It should be more expensive because it has more gold in it. And so that was interesting that for some reason we don't use as much gold in our gold jewelry as they do. So it's kind of interesting. But it's the alloys. Metallurgy is a pretty neat field. I mean, it's really, and jewelry is metallurgy. I mean, that's what a lot of jewelry is, and it's, or the study of that. And it's pretty cool. So tell me about nonmetals, and don't say opposite. Don't just say the opposite. I want words that mean the opposite. Let's start off the same. Most are gases at room temperature. Who's the exception? Bromine is what? Is liquid. Others are solid. So most are gas at room temperature. I didn't put the word temp. Most are gas at room temp. Bromine's liquid. Others are solid. Now, they're not good conductors of heat and electricity. What are they good at? Say it. Somebody said the word. Insulators. They're good insulators. Good insulators. They're good insulators. They are not shiny. They are dull. They are not malleable and ductile. They are, say it again, brittle. They're brittle. They're brittle. They break easily. So those are some characteristics of nonmetals. Metalloids, I will use in a sense of cheating. We're going to simply say intermediate properties, and they do. They have a mix of properties. Metalloids have intermediate properties. For instance, silicon and germanium are semiconductors used in electronics. Silicon and germanium are used a lot in computer chips. What is the place in California called that has something to do with this? Does anybody know? Silicon Valley. You know, that's so fun that you guys know that. For several years when I would ask that question, students didn't know what I was talking about. And I thought that was odd, but then now the fact that you do know it is even odder to me that you know it again. When I was in high school, that's when computers first, like we might in my high school have had, I graduated in 89, and I'm thinking that we had computer lab, maybe one computer lab, or maybe have just gotten computers in 89. I bought a computer when I came to college, but I was one of the few people who actually had a personal computer. And back then, that's when a desktop computer cost like, I don't know, it was a really expensive, $3,000 maybe, and it's like you save all your money and you put it into that computer. And then now it's just amazing. But back then, Silicon Valley was talked about a lot because that was huge. I mean, computers just came out. But it's funny that you all know that when that group of people didn't know it. I found that interesting that you guys have heard that. But why do they call it that? Because that's what they use. And where was basically the birthplace of computers? In Silicon Valley. That's the birth, I mean, that's basically where it was. So it's kind of interesting. All right, so those are this is metal, nonmetal, metalloids. That system is one way we can identify elements. Solid, liquid, gas is another way we can identify elements. So I might ask a question, for instance, that says something like, which of the following elements is a metal solid at room temperature in period whatever? And I'm not looking, so I'm not going to tell you exactly what that would be. But the point is you have to know what the state is of the elements, and you need to know where they are on the periodic table and whether they're metal, nonmetal, or metalloid. Those are things that you need to know and be able to identify on the periodic table. What is in your body? You heard this before? What is it? CHON? Have you heard of CHON before? Anybody ever said CHON to you before? What does that stand for? Carbon, hydrogen, oxygen, and nitrogen. Which one of those is the most abundant? Does anybody know? You have 4 choices. Carbon is not. Say it again. Nitrogen is not. Oxygen is. Oxygen is. Oxygen is the most abundant. Oxygen is the most abundant. And then it is in order of carbon, hydrogen, and nitrogen. So it is in the order of CHON except for oxygen is the most abundant. Tell me how oxygen can be the most abundant. Okay, people say it's in the blood. That's not why it's the most abundant, though. Take another guess. Say it again. Who's saying that? They're right. Water. You're right. You're right. That's it. Usually takes more guesses. Most people say, then the lungs. They'll say the lungs. It's the water. Guys, what are we mainly? Water. I love telling people, I'm not overweight. I'm well hydrated. I mean, seriously.
There's hydrogen in water, too.
Sure there is. I know. You've stolen my little story. You're right, because that's what everybody says. Well, how can it be? How can water, we're mainly water, but I'm telling you we are mainly oxygen, but water is H2O. It looks like it's twice as much hydrogen as it is oxygen. But this is by mass. Hydrogen has a mass of 1.01 is how we are going to round it. Oxygen has a mass of 16. So that means one oxygen is 16 times heavier than one hydrogen. So even though it has 2 hydrogens, oxygen is still a whole lot heavier. In fact, water, if you just have pure water, water is about 88% oxygen and only about 12% hydrogen. And so if we are mainly water, which we are, then we are mainly oxygen, because water is mainly oxygen. And then it's carbon, and yes, we are a lot of carbon, and we're a lot of hydrogen and a lot of nitrogen. The other, and this is true for all living matter. All living matter is made up of carbon, hydrogen, oxygen, and nitrogen, and oxygen is usually the most abundant. In most situations, oxygen will be the most abundant. The rest of what is in our body is listed here. Now, I will never ask you any of these from this illustration. I will never ask you, give me the major minerals, the minor minerals. I will never ask you that. Other than I will ask you about the 4, but I won't ask you about anything else. Why do I even show you? Because I have such a great mix in this room. I have nursing majors who should be interested in all this. I have exercise science majors who should also be interested in especially the major minerals. And if you are truly into your body, you also need to be aware of the trace minerals. I also have dental hygiene majors who, yes, also ought to be interested in all of these, because what makes up your bones and your teeth? Calcium and phosphorus. For those exercise science guys, you know that you need the protein. And I say guys, girls too. You know that you need the protein in order to build muscle mass because this is protein, and you know that you need to add protein in order to bake more protein. You understand that. You probably understand nitrogen is part of protein. That's usually what people understand. But did you know that it also takes magnesium and sulfur? Those are things probably you didn't realize that you needed. And so all of this is pretty cool and interesting for all of us. The other thing, how many of you have ever worked in a nursing home or are working in a nursing home? Do I have? Good. What have you seen in your elderly patients are the two minerals or elements, whatever you want to call them, that they meaning elderly people, struggle with maintaining? Say it. Well, calcium is not the one I've actually heard of the most. Calcium I definitely think would be affecting their body. Let me tell you the scenario I'm trying to describe, because some of you I know have experienced this. You may have a patient who seems to be doing fine, and then within a day or two they are extremely weak, and their memory and their brain is just like they're just like lost it. Potassium and sodium. Some of you know, you've seen this. Some of you have seen this. Low potassium and low sodium affect their muscles, their heart, and their brain. Because all of that, muscle contractions, heart, and brain, all run on an electric system, basically. Yes? Does that make sense? So if you don't have those calcium, probably too, potassium and sodium especially, when they get low, their body goes wacko. And it can do it almost like that. If they are on a diuretic, meaning something to flush their system of water, and they're not eating much, it can affect them drastically compared to those of us that eat normally. And so it's really one of those things we have to watch for. So again, not something I'm ever going to test you on as far as these two categories. CHON, yes. The others, no. Now, the subatomic particles, like I said, I bet you've had this for a long time, so let's quickly go through these. Who are they? Protons, electrons, and neutrons, okay? What's the charge of protons? +1. Electrons? -1. Neutrons? Neutral neutrons. 0. Symbol for protons is P or positive. Electrons is E negative, and neutrons is N. The relative mass is 1 AMU for a proton, negligible for an electron, and 1 AMU for a neutron. Protons. Let me tell you a little bit about protons. Protons give positive charge to the nucleus. And give mass. They give a positive charge to the nucleus and give mass. Electrons give negative balance to that positive nucleus. They give that negative balance to the positive nucleus. I want to add a little bit more to that. In a neutral atom, protons equal electrons. And then neutrons are the mass. Mass minus protons equal neutrons. Mass minus protons will equal the neutrons. For our purposes, we will always round neutrons to a whole number. But mass may not be rounded to a whole number. That's why I put that. We will round neutrons to a whole number, but mass may not be. So let's talk about mass first. Let's go down here and talk about mass. Atomic mass is symbolized as A. I didn't make that up. Someone else did. But atomic mass is symbolized by A, and it is what? What makes up the mass? Protons plus neutrons. So protons plus neutrons make up the mass of an atom. Protons plus neutrons. If you get the mass from the periodic table, I have a rule, and that rule is round it to the nearest hundredth. So in my class, on my test, everything else, round to the nearest hundredth. That's 2 decimal places. That way we're all the same. What is the atomic number? It's the number of protons. Atomic number is equal to the number of protons. Atomic number is equal to the number of protons. Take it down and then back up. Atomic number is the identity of the atom, so it cannot change. Atomic number is the identity of the atom. It cannot change. So before we go any further and talk about ions, let's stop. Who is atom 35? Bromine. Who is atom 23? Vanadium. Vanadium. All right. What is the number of protons of lithium? 3. What is the number of electrons in neutral chlorine? 17, because it's the same as protons. You with me? Okay. Now then, let's talk about ions. Protons are equal to electrons in a neutral atom. But when an atom has lost or gained electrons, it's no longer neutral. Let me go backwards, though. Why can't protons change? That changes the element. Protons never change. So you can't add protons, meaning you can't add positive, you can't lose positive. Positives always stay the same. The only thing you can change are the electrons, which are negative. So let me ask you a question. This will make sense to you. If you surround yourself by negative people, what do you become? Negative. If you lose those negative people, what do you become? Then just remember that. Ions are charged atoms due to a loss or gain of electrons. A cation is a positive ion due to what? Loss of electrons. Anions are negative ion due to what? Gain of electrons. Remember, if you gain negatives, you become negative. If you lose negatives, you become positive. That means if an ion has a positive 1 charge, how did it get that positive 1 charge? It lost 1 electron. If an atom has, or an ion rather, has a negative 3 charge, how did it get that negative 3 charge? Negative 3 charge. Gained 3 electrons. Does that make sense? Okay. All right then. Do it. Do you know it? Do it. So come over here and let's dissect these particles. I'll do this one with you. Sodium. Tell me what you know about sodium. What's the number of protons for sodium? 11. Who else automatically is 11? Well, automatically always. Atomic number. That one's always atomic number. So automatically protons and atomic number are always the same. Always. So that's 11. Now, because this is neutral, how many electrons are there? 11. All right, what's the mass? What's the mass? Round properly. Do you all remember the day I taught rounding? And I told you these were the most missed rounded, and that was the first one. And people did what I said people would do. You rounded it to 23. What is it? 22.99. 22.99. So it's 22.99 AMU. Something I did not do that I need to do, you probably want to have this in your notes somewhere. I didn't tell you what AMU stood for. Anybody know? Atomic mass unit. It's just a generic term, but it stands for atomic mass unit. Atomic mass unit. All right, so it's 22.99 AMU. That means neutrons, we're going to round this to a whole number, and that's 23 minus 11 is what? How many neutrons? Come on, 23 minus 11. 12? I hope. Okay. All right, I'll do phosphide with you. Protons. Look at your periodic table, guys. You've got a periodic table. You just labeled it. 15. Who else automatically is 15? Atomic number. How many electrons? Be careful. 18. Why is it 18? Because it gained 3. The name of this is phosphide. It has a negative 3 charge. How did it become negative 3? It gained 3. Now, somebody out there is thinking where they come from. It doesn't matter right now where they come from, okay? I'll tell you that later. And somebody else is saying, well, where are they going to go? I'll tell you that later. It doesn't matter right now. Just know that they are lost or gained from somewhere and they go somewhere. But if you gain negatives, you become negative. So if you gain 3, you become negative 3. What's the mass? 30.97 AMU. Good. And then neutrons, how will we do that? How do we do it, though? 31 minus 15, which is 16. 16. All right, you do the next 3. You do these 3. Guys, use your periodic table. It's easier to see. All right, what do you have for iron protons? All right, what else is 26? Atomic number, good. Are the electrons the same as the protons? No. How many electrons are there? 24. Why? It's lost 2 because it has what charge? Plus 2. It has a plus 2 charge. That means it's lost 2. Good. What's the mass? It's 55.85, rounded properly, AMU. 55.85 AMU. And then 56 minus 26 is what? 30 neutrons. All right, tell me, actually though, let me, before we go any further, what's the name? Make this easy. This is the name I told you. If it's a transition metal, it's iron 2. The Roman numeral is the same as the what? Charge. Now, anybody want to tell me that had chemistry maybe if you know the old name? Because you're also going to need to know that. You may know the old name? Ferrous. The old name is ferrous. The old name is ferrous. We'll talk more about why I'm having you learn those. All right, tell me about 10. 50 protons. What else is 50? Atomic number. And this time what? Electrons are also 50 because it's neutral. What's the atomic mass? 118.71 AMU. And then 119 minus 50 is 69. Good. This is called simply, since it's a metal ion, what's it simply called? Say it. Barium. It's just barium. It's the same as the name, and you can put barium ion just to indicate that it is an ion. What is the number of protons? What else is 56? The atomic number. How many electrons? 54. Mass? 137.33 AMU. And then 137 minus 56 is what? 81. Yes or no on those? Okay. All right, couple more things about the atom. We haven't talked much about the nucleus, so let's talk about the nucleus. The nucleus of the atom contains protons and neutrons. The nucleus of the atom contains protons and neutrons. It has a positive charge. Why? Because protons are positive. Are the protons in the nucleus? Neutrons have what charge? None. So it's going to be what charge? Positive. It would be positive charge. Tell me about the mass of the nucleus. Does it have all the mass? What's in it? So does it have all the mass? Yes, pretty much, yes. When I said that the electrons are negligible, that means they don't have enough mass to worry about. Negligible means not enough to worry about, okay? So it has all the mass. All the mass is there in the nucleus. Yes?
Okay, so if like protons and neutrons equal 1 AMU,
Each protons equals 1 AMU and neutrons equal 1 AMU, yes.
So why is it that the atomic mass is like decimal?
Because the atomic masses that we really see on the periodic table are grams per mole, which, again, electrons are negligible, but they have a little bit. And so it's like 10 to the negative something grams. I don't remember what it is. Your book has it, I'm sure. It's in your book. We don't worry about the actual mass right now. We're looking at relative, and that's what atomic mass units are. They correspond to AMU and grams correspond, but for our purposes, they're negligible. Okay? Now, the thing you don't know, you knew all the mass was there. You knew it was positive. What you don't know is that the nucleus is very tiny. If something has all the mass, but it's tiny, what is it? It's very dense. Very tiny and very dense. To give you an idea of the relationship of the nucleus to the atom, imagine a green pea in the center of the 50-yard line on a football field. That's the nucleus. All the rest of the football field is the rest of the atom. So where's all the mass in that little green pea? That means that is extremely dense. Okay? That's kind of the picture, which also tells us then that most of an atom is empty space. So what's in that empty space? For right now, today, we're calling that the electron cloud. And the electron cloud surrounds the nucleus and contains the electrons in constant motion. Those electrons are constantly moving. Wednesday, or Thursday rather, of this week, we are going to mainly focus on the nucleus, nuclear chemistry. We're doing preschool nuclear chemistry, okay? Very, very minor nuclear chemistry that we're focusing on. One day nuclear chemistry. Tuesday of next week, we're going to focus on the electron cloud and really break that down into what's called the quantum theory. At this point right now, our knowledge of the atom, and some of you, let me say, in this class, our knowledge of the atom. If you've had high school chemistry, you know more. But at this point, what I've taught you, the basics of the atom that I have taught you, and this is what early chemists and early physicists and early atomic theorists said. They said, okay, here's the nucleus of the atom, and you're going to see me do this a lot over the next 2 weeks. I use my body a lot in this. But I always point to my belly button. I'm like, okay, there's the nucleus, and then all this around the nucleus is the electron cloud. That's what we know right now. Next week, we're going to find out exactly where these electrons are in the electron cloud for all the atoms on the entire periodic table. If you had chemistry, you heard this before, and it was called quantum theory, electron configuration notation, 1s2, 2s2, 2p6, 3s. Some of you are nodding your head. You've heard this before. That's going to build us up to basically why are the noble gases called noble gases? Why do these ions have the charges they have? Why do they form compounds like they do? How do they fit together and make these different shapes that they make? All that's going to kind of be pulled together, and it will make a lot of sense next week once we get it together. But right now, we are in history saying this is all we know about the atom so far, okay? Those early chemists also thought that all atoms of the same element were exactly alike. But we found out, no, they're not. In other words, they thought all atoms of carbon were exactly alike. But all atoms of carbon are not alike. Carbon can have different mass. Anybody know what that's called when they have different mass? It's the next word. Isotopes. You heard of isotopes? Some of you have. So what is an isotope? An isotope is an atom of the same element that has different mass due to different I'm going to let you finish. An atom of the same element that has different mass due to different what makes up mass? Protons and neutrons. What can't change? So then what's the only thing that the answer could be? Neutrons. Due to different number of neutrons. That means, can neutrons change? Yes, neutrons can change. You know, I always think of neutrons as fat. I mean, that's not what they are. But neutrons are like the fat of the atom. They just change the mass. They don't have a charge. They just simply change the mass. That's what neutrons do. The mass that you and I see on the periodic table is not of one particular isotope, though. The mass that we see on the periodic table is an average. It's an average mass of all known isotopes of that atom. And it's actually an average that's based on abundance. To give you an example, hydrogen has 3 known isotopes. And I'm going to name them for you in just a minute, but I'm just going to talk about them right now. Hydrogen has 3 known isotopes. They have masses of 1, 2, and 3. Which one of those must be the most abundant? 1. How do you know that? What's the average closest to? 1. Does that make sense? Carbon has, to my knowledge, carbon has 3 known isotopes. Carbon 12, carbon 13, carbon 14. Again, which one of those is the most abundant? Carbon 12. Now, every scenario I'm giving you happens to be the one that's the lowest. That's just unusual, but it's still there. Iodine has an isotope called iodine-131 that is used to treat hyperthyroidism and sometimes thyroid cancer. Do you think iodine-131 is very abundant? Look at the periodic table and tell me. Do you think iodine-131 is very abundant? No. Why? What's the average closest to? Or what is the average? It's not anywhere near 131, is it? So very likely it's not very abundant. It's not very abundant. And so it's, in our case, if I were to explain isotopes, or when I do try to explain isotopes, one of the ways I explain it is using us. What is one word that describes all of us, including me, all of us? What's one word? What are we all? People or human. That's usually what I get. People or human. So let's say that we are all the element people. Our symbol is PP. We are all people. Our symbol is PP up on the periodic table. And I have done this before. I'm not going to do it today. But in the past, I've actually had students write down anonymously their weight. And they sent it to me, and I averaged it, and it was 165 pounds. So up on the board, or up on the periodic table, I'd put 165 for our mass. I don't know what our atomic number would be, but I'd put our mass up there. Now, in our case, I'm doing an average that's not based upon abundance. I'm just doing a blanket average. They have averages based on abundance. But both scenarios apply. If I said to you that our average is 165, does that mean that any one of you have to have a mass of 165? No. It just means that the average is 165. And what is 165? That means that is our protons plus our neutrons. All of us have some similarities, though, don't we? We all have one head. We all have two eyes, two nostrils, two arms, two legs, one heart. You with me? So are we all the same? Yes. But are we all different? Yes. And we are very special because we are named isotopes. We're very special isotopes. Most isotopes are not named. Hydrogen, though, also has some named isotopes. So it's got some special isotopes. They are named protium, deuterium, and tritium. Protium, deuterium, and tritium. And already I told you the masses of those. So let me write that down. We're going to look at the mass, we're going to look at protons, and we're going to look at neutrons. The mass of protium is 1 AMU. What's deuterium? 2 AMU, and tritium is 3 AMU. Do you understand the names now? Okay. How many protons does protium have? Why? Because it's who? It's hydrogen. How many protons does deuterium have? 1. Why? It's hydrogen. How many protons does tritium have? 1. Because it's hydrogen. So what changes? Neutrons. Because 1 plus the neutron, 1 plus will equal the mass. So let's start with tritium. How many neutrons does tritium have? 2. Deuterium, 1, and protium, 0. You mean you can have no neutrons? Sure. You don't have to have neutrons. You don't have to have neutrons. Now, where have you heard these before? Where have you heard about these? Have any of you ever heard about any of these before? No, not to my knowledge. They are in reactions. If you've had an astronomy class, you might have heard of them. One of them, maybe 2 of them. If you go to the planetarium, and that's a free, cheap date. If you want to go to the planetarium and watch the star show, it's actually pretty interesting. And you will hear about deuterium there because the forming of stars is actually when it is a nuclear reaction that actually takes place to form a star. And deuterium is involved. And they join together 2 nuclei to form a heavier nuclei. And that's where the sun's energy comes from. So you will find that out about deuterium if you go to there. Have you heard of tritium before? Has anyone ever heard of tritium? Anybody ever heard of tritium? Do I have any military folk or former military folk? Nope. Nobody's ever heard of tritium? It was funny yesterday in my second class. In my first class, I had a military person, and they had known about tritium because of that. The second class, though, one of the students said, yeah, I've heard about the tritium vial. I'm like, what? You can get a vial of tritium? And he's like, yeah, I don't know where, but I know I've heard about it. You could get a vial of tritium. I'm like, that's cool. And so I was excited about that. Here's what I know about tritium. Because if I were you, I'd be like, these really don't even exist. They do, and this one is cool. Tritium is really cool. So let me go backwards, though. What is in this room that if the lights went out, you would want to find? You just looked at it. The exit sign. You'd want to know how to get out. What's that exit sign require? Electricity? Okay. So if the whole electricity out is in this, if the whole building has no electricity, how are you going to see to get out of this building? I know somebody's going to say the generator comes on, and you're right, it would. But There are exit signs. I mean, that's like the biggest thing you would want to know how to get out of a room, right? I mean, this room, honestly, would be kind of hard to not get hurt to get out of if it were pitch black. You would get hurt getting out of this room. You may not. I'm not going to get hurt, but they're going to get hurt climbing over, right? So we're going to get out. But the point is you want to know how to get out if there's no electricity. Exit signs are made with tritium in them. Not all. No, I'm not saying these have tritium. These don't have tritium. That doesn't have an exit sign. That's interesting. All the other rooms in this building have exit signs on both doors. I didn't even pay attention to that until just now. But there are exit signs that contain tritium. And it's really neat because they do not use energy. They are no energy exit signs. And they have 20 and 30 and more year warranties, like a 30-year warranty, because tritium, as it decays, gives off light. It gives off energy in the form of light. That's why that student was telling me about the tritium bile. It glows. And so it gives off energy in the form of light. And so you can look these up. And you can get these exit signs that have no energy usage that you just put up, and they'll last 20 or 30 years, and they'll give off the right amount of lumens of light so that you can see to get out of the building. The funniest thing for me personally is, how did I even ever know about that, was because I feel like I've lived too many lives when I haven't lived but one life, but I forget I did that. When you live long enough, you're like, did I really do that, or did I just dream I did that? Well, I really did this. There was a time period that we were looking at expanding our business, and one of the things we looked at doing were selling energy-saving products. And the energy-saving product that we were looking at selling was exit signs. We were looking at selling those. The funniest thing is this was like 20, 25 years ago, which was way before energy conservation was popular. We were like ahead of our time. Then we didn't do it. Now everybody's into energy savings. And so it's kind of funny. But look it up. It really is. You can Google it now and find them. But you can find tritium exit signs, and they really are real. So pretty cool. The reason I ask about the military is because in the military, they actually have compasses that glow because they're tritium. They have tritium inside of them.
That was my question.
Okay, did you know about them?
No, I was just
Okay.
what I had to do.
Yeah, because they have those, and then they also, the students have told me, scopes. Some of their scopes have tritium in them. Did you know that? Yeah. Do you know of anything else that has tritium? Yeah. Were you in the military? Oh, yeah. But anyway, students have told me that because I didn't know about those. I just knew about the exit signs. All right, so how do we indicate that we have isotopes? Well, there's two different ways. One of them you actually already have heard me say, and so I'm going to do the second one first. We use the name and the symbol of the element and the isotope mass. Use the name, and I put and, make that or. Use the name or the symbol of the element and the isotope mass. So example, iodine-131. What does that mean? That means it's iodine with a mass of 131. Or if I do carbon-14, what's that mean? Carbon with a mass of 14. You may have heard about U-238 or U-239 or U-235. That's uranium. That's your nuclear reactor. Uranium with a mass of 238. That's what those are. That's the simple one. That's the one if you read the newspaper and it's got anything about nuclear, you're going to see it there. That's what you would see there. But there's also what we call the isotope symbol. And the isotope symbol uses the symbol of the element and the mass and atomic number. And the mass is actually a superscript on the symbol, and the atomic number is a subscript. So I'm going to show you, this is the generic isotope symbol. So if you have the symbol X then you have the mass in the top left-hand corner and the atomic number in the bottom. So let us write the isotope symbol for protium, deuterium, and tritium. What's the symbol? H. Why? It's hydrogen. Every time, it's hydrogen. All three of these are hydrogen. Now, what is the mass of protium? 1. What's the atomic number? 1. Deuterium, what's the mass? 2. What's the atomic number? 1. Tritium, what's the mass? 3. What's the atomic number? 1. Does that make sense, what we're doing? So now, on these, I want us to write the isotope symbol for the isotopes that have these characteristics. Now, how are you going to know who it is? Protons. So who is this? Use your periodic table. Who is this? This is 10. So you're going to put S in. And then how do you get the mass? Protons plus neutrons. Don't get the mass off the periodic table. We're not using periodic table mass. These are these isotopes. So we get the mass here. What's the mass? 118. And then what goes down here? Why? That's the atomic number. Now there's one more thing you have to do though. Are the electrons and the protons the same? Yes, they are. So is this an ion? No, this is not an ion. Yes or no? Okay. So now then, go to this side. Who's this? So this is iodine. What's the mass? I love your math skills. 125. What goes at the bottom? 53. Then you look and say, okay, is there a difference between electrons and protons? Okay, so what do I put here? -1 or 1 minus. It doesn't matter. Properly, it is 1 negative, but if you put -1, I'm okay with that. So this is an ion that's an isotope, and that's okay. It can be that. All right, let's go to the one below it. Who is this? Who is this? Barium. What's the mass? 136. What goes on the bottom? 56. Is it an ion? What's its charge? 2 plus. All right, do the rest of these right now. Do the rest of these. Did everyone get the sign-in sheet? Can somebody pass it back down here, please? All right, who is this? Uranium. Who is this? Uranium who? Uranium-239. Good. What goes down here? Is this an ion? No. Okay, who is this? Carbon who? Carbon-14. And what goes here? 6. Is it an ion? Okay, who is this? Nickel. Its mass is 59. 28. Is it an ion? So it's really nickel 59, that is nickel 2. Right? So it's got the charge of +2, but it's got an isotope mass of 59. This is something that you probably would see if you were in the field of nuclear medicine in some form or fashion. You would probably see these. Normal folks are going to see them written this way. Okay? Now then, I am done with lecture, but I'm not done with you. So just listen to me for a minute, okay? There's something I want to do. You can cut it if you want.